There is a law written into the fabric of reality itself. Not a law passed by parliaments or inscribed on stone tablets, but a law more absolute than gravity, more unforgiving than time. It is the second law of thermodynamics, and it states, with mathematical certainty, that entropy always increases. Always. Without exception. Without mercy. You feel it every day, though you may not name it. The coffee that grows cold in your cup. The battery that drains in your phone. The wrinkles that etch themselves deeper into your skin with each passing year. These are not accidents. These are not failures of engineering or biology. These are manifestations of the universe's most fundamental directive. Everything that is ordered must become disordered. Everything that is warm must grow cold. Everything that moves must eventually stop. And this law does not confine itself to coffee cups and human bodies. It extends to stars, to galaxies, to the cosmos itself. Given enough time, and the universe has infinite time, every structure will crumble, every fire will die, every light will fade into an eternal, uniform darkness. This is not speculation. This is not philosophy. This is physics, as certain as the ground beneath your feet. Welcome to the story of the heat death of the universe. The slow, inevitable march toward the final silence of the cosmos. Imagine you are watching a film of a glass falling from a table. It tumbles through the air, strikes the floor, and shatters into 1,000 glittering pieces. Now imagine that film played in reverse. The shards leap up from the ground, assembling themselves with impossible precision, reforming into a perfect glass that rises gracefully back onto the table. You know, instantly, that the second scenario is wrong. Not just unlikely, fundamentally, viscerally wrong. But why? The laws of motion governing each individual molecule are time reversible. Newton's equations work just as well forwards as backwards. At the quantum level, the fundamental interactions don't prefer one direction over another. So why does the universe? The answer is entropy. Entropy is often described as disorder, but this is an insufficient metaphor. Entropy is better understood as the number of possible microstates, the number of different ways particles can be arranged that correspond to a given macrostate, the overall configuration we observe. A whole glass represents one macrostate with relatively few microstates. The molecules must be arranged in a very specific crystal lattice. But a shattered glass. The pieces can be scattered in countless ways, billions upon billions of configurations, all of which look more or less the same to us, broken. The second law of thermodynamics states that isolated systems evolve towards states with higher entropy, not because nature prefers disorder, but because there are simply more ways to be disordered than ordered. It's not a conspiracy. It's statistics. If you shuffle a deck of cards randomly, you're far more likely to produce a disordered sequence than to accidentally arrange them perfectly by suit and rank. Not because disorder is better, but because disorder is more numerous. This is the arrow of time. Not time itself. Time may be a dimension like space, stretching in both directions, but the arrow, the directionality, the fact that we remember yesterday but not tomorrow, that we age but never youngen, that we can scramble eggs but never unscramble them. All of this flows from entropy's relentless increase. And this arrow, once loosed, never turns back. Not in this universe. Not in any universe governed by the laws we know. Every process you observe, every change that occurs, is a small victory for entropy. When you burn wood, ordered chemical bonds break down into disordered heat and gas. When you think a thought, your neurons convert organized glucose and oxygen into scattered carbon dioxide and waste heat. When a star fuses hydrogen into helium, it transforms concentrated nuclear energy into diffuse radiation that spreads across light years of empty space. You might think you're fighting entropy. You clean your room, organize your files, build skyscrapers and spacecraft. But look closer. Every act of local organization requires a greater act of global disorganization. Your body maintains its structure only by consuming food and radiating heat into the environment. Your room becomes orderly only because you've burned calories, which came from plants or animals that captured energy from the sun, which is itself burning through its fuel and increasing the universe's total entropy by staggering amounts. You are not fighting entropy. You are entropy's instrument. Everything you do, everything you create, every thought you think increases the universe's disorder. You are an entropy engine wrapped in skin, and you cannot turn off. This might sound like nihilism, but it is simply physics. And physics, unlike philosophy, does not care what you think about it. In the winter of 1906, a brilliant man walked into the woods near Duino, Italy, and hanged himself from a tree. His name was Ludwig Boltzmann, and he had seen further into the machinery of reality than perhaps any human before him. That vision destroyed him. Boltzmann was born in 1844, in an age when physics seemed almost complete. The laws of thermodynamics had been formulated. Heat engines were revolutionizing industry. But there was a problem, a deep conceptual crack in the foundation. Nobody understood why heat always flowed from hot to cold, why entropy always increased. It seemed to violate the time reversibility of Newton's laws. Boltzmann proposed something radical. Entropy was not a property of energy itself, but a property of information, or rather, the lack of it. At the microscopic level, every system consisted of countless particles moving according to reversible laws. But at the macroscopic level, we couldn't track every particle. We could only see averages. Entropy, Boltzmann argued, was a measure of our ignorance about the exact microstate of a system. His equation, carved on his gravestone in Vienna, is deceptively simple. S equals K log W. Entropy equals Boltzmann's constant times the logarithm of the number of microstates. Elegant, revolutionary, and rejected by almost everyone. The physics establishment of his time found Boltzmann's statistical approach disturbing, even offensive. Ernst Mach, one of the most influential physicists of the era, didn't even believe atoms existed. How could statistical mechanics based on atomic behavior be taken seriously? Boltzmann was ridiculed, isolated, driven to the margins of academic life. But there was something else eating at him, something deeper than professional rejection. Boltzmann's own theory implied something horrifying. If entropy increase was merely statistical, merely probable rather than absolute, then in principle, entropy could decrease. Given enough time, random fluctuations could spontaneously reorganize scattered molecules back into ordered states. A shattered glass could, by pure chance, reassemble itself. The probability was infinitesimally small, but it was not zero. This led Boltzmann to a disturbing thought experiment. If the universe had infinite time, then eventually, by pure random chance, regions of low entropy would spontaneously form within the high entropy background. These regions, fluctuations from equilibrium, would be rare, but they would happen. And if they happened, observers would naturally find themselves in these low entropy regions, because only low entropy regions could support complex structures like stars, planets, and life. But here's the nightmare. The most probable fluctuation that could support an observer is not an entire universe, not even an entire galaxy. It's just a single brain, spontaneously assembled by chance, complete with false memories of a past that never happened, floating in a void and doomed to dissolve back into chaos within seconds. These hypothetical constructs would later be called Boltzmann brains, and they represented a kind of reductio ad absurdum of his own theory. If Boltzmann was right, then statistically, you are far more likely to be one of these phantom brains hallucinating a consistent universe than an actual person in an actual cosmos. Your memories are lies. Your observations are delusions. You are a ghost flickering briefly in the entropic void. Boltzmann wrestled with these demons, both metaphorical and literal, for decades. He suffered from bipolar disorder, enduring cycles of manic productivity and crushing depression. His theory, while brilliant, offered him no comfort. Instead, it seemed to dissolve the reality of existence itself into probabilistic shadows. In 1906, while vacationing with his family, Boltzmann's depression overwhelmed him. He left his wife and daughter at their lodgings, walked into the forest, and ended his life. Within a few years, experiments would confirm the existence of atoms. Einstein's work on Brownian motion would vindicate Boltzmann's statistical approach. His equation would become a cornerstone of modern physics, appearing in textbooks worldwide. But Boltzmann would never know. He died believing he had failed, never realizing he had seen the future. His epitaph might as well have been written in entropy itself, a brilliant mind dissipating into silence, a local decrease in disorder overwhelmed by the universe's inexorable increase. Even genius cannot escape the second law. But his vision remained, etched not just on his tombstone but into the structure of physics itself. Entropy was real. Its increase was inevitable. And given enough time, it would claim everything. Even the stars. 13.8 billion years ago, the universe exploded into existence. Not into space. There was no space. Not at a location. There was no location. Space and time themselves unfurled from a singularity of infinite density and temperature, expanding at speeds that make light seem frozen in comparison. This was the Big Bang, and it was not a beginning. It was a deviation. Because here's what's strange. The early universe was in a state of extraordinarily low entropy. This seems paradoxical. How could something infinitely hot and dense be low entropy? Isn't a gas of particles at maximum temperature the definition of high entropy? Not in a gravitating universe. In systems dominated by gravity, entropy behaves counterintuitively. A uniform gas spread evenly through space is actually a low-entropy state for a gravitating system, because gravity wants to pull things together. High entropy, in this context, means massive structures, stars, black holes, ultimately black holes containing everything. The early universe, that smooth, nearly uniform plasma, was as far from equilibrium as it could possibly be. This is the cosmological puzzle that haunted Boltzmann and still haunts cosmologists today. Why did the universe start in such a special, low-entropy state? It's like finding a shattered glass spontaneously reassemble itself, except the glass is the entire cosmos. Some invoke inflation, that brief period of exponential expansion in the first fraction of a second, which smoothed out irregularities and set up the initial conditions. But this only pushes the problem back. Why did inflation start in a low-entropy state? Others suggest the Big Bang itself might be explained by quantum fluctuations or colliding brands in higher dimensions, but these too require special initial conditions. The anthropic principle offers a different answer. Perhaps there are countless universes with all possible initial conditions, and we necessarily find ourselves in one of the rare low-entropy ones because only those can support observers. It's a profoundly unsatisfying answer. It explains everything by explaining nothing, but it may be the only answer available. Regardless of why it started, the crucial point is that it did. The universe began with vast reserves of usable energy, enormous gravitational potential, and that smooth distribution of matter that was desperately out of equilibrium. And immediately, inexorably, entropy began its work. First came nucleosynthesis, the forging of light elements in the primordial furnace. Protons and neutrons, previously free, combined into hydrogen and helium nuclei. Order emerged from chaos, but only because tremendous amounts of heat were being radiated away. Entropy increased. Then came recombination, when the universe cooled enough for electrons to bind to nuclei, forming the first neutral atoms. Light and matter decoupled. The universe became transparent. We see this moment today as the cosmic microwave background, that faint glow of ancient light now stretched into microwave wavelengths by cosmic expansion. It is the afterglow of creation, and it is also entropy made visible, energy spreading, diluting, growing cold. But within this expanding, cooling universe, something remarkable happened. Tiny fluctuations in density, quantum ripples from the inflationary epoch, began to grow. Where matter was slightly denser, gravity pulled more matter. Where it was slightly less dense, matter drained away. The universe's smooth uniformity began to fracture into structure. This was gravity's rebellion against thermal equilibrium. While heat wanted to spread everything out uniformly, gravity wanted to pull everything together. Over millions of years, those tiny density fluctuations grew into vast cosmic webs, filaments and sheets of dark matter hundreds of millions of light-years across, separated by voids of near emptiness. Where these filaments intersected, where matter pooled most densely, the first stars ignited. This happened roughly 100 million years after the Big Bang, in what astronomers call the cosmic dawn. Clouds of hydrogen gas, drawn together by gravity's patient hand, compressed and heated until nuclear fusion ignited in their cores. Light pierced the darkness for the first time since recombination. The universe lit up. These first stars were monsters, hundreds of times more massive than our Sun, burning with savage intensity. They lived fast and died young, exploding as supernovae that enriched the cosmos with heavier elements. From their ashes, new generations of stars formed, smaller and longer-lived, surrounded by planets, some of which would one day support life. It looked like creation. It looked like order emerging from chaos, complexity fighting back against the void. But it was an illusion. Every star that ignited was not a victory against entropy but an acceleration of it. Gravity might have created local order by pulling matter together, but it did so at an enormous entropic cost. The fusion reactions in stellar cores transformed ordered nuclear energy into scattered photons that radiated across the cosmos, heating the universe's background temperature infinitesimally but irreversibly. The universe was building structures, yes, galaxies and stars and planets, but only by burning through the gravitational potential energy established at the Big Bang. It was spending its inheritance. And that inheritance, while vast, was finite. The universe was not defeating entropy. It was delaying the inevitable. And with every star that lit the darkness, with every galaxy that wheeled through space, the final day drew closer. The cosmos had remembered it was going to die. And now, it had begun the long process of dying. A star is a furnace held together by its own weight. In its core, hydrogen fuses into helium at temperatures of 15 million degrees, releasing energy that prevents the star from collapsing under its own gravity. This is equilibrium, not static, but dynamic. The star is constantly trying to crush itself, and nuclear fire is constantly pushing back. But this equilibrium is temporary, because fusion is not free energy, it's borrowed time. Every time 4 hydrogen nuclei fuse into one helium nucleus, a tiny amount of mass, about 0.7%, is converted into energy according to Einstein's famous equation. That energy radiates out as light and heat, warming planets, driving photosynthesis, creating the conditions for life. From our perspective, stars are sources of order, beacons of negentropy in an entropic universe. But zoom out. Look at the bigger picture. That radiated energy doesn't disappear. Energy is conserved, but it does become useless. Concentrated nuclear energy, capable of doing work, transforms into diffuse thermal radiation spreading through the cosmos. The energy is still there, but it's no longer organized. It can no longer be harnessed. This is entropy increase in its purest form, the degradation of useful energy into useless heat. A star, then, is not a creator. It's a converter. It takes the low-entropy fuel of nuclear binding energy and converts it into high-entropy radiation. It is an entropy engine, and it cannot run forever. The smallest stars, the red dwarfs, burn so slowly they could theoretically last for 10 trillion years, 1,000 times the current age of the universe. They sip their hydrogen fuel in tiny sips, fusing it at temperatures barely high enough to sustain reactions. When the universe is 10 trillion years old, when every other type of star has long since died, red dwarfs will still be burning, faint embers in an otherwise darkened cosmos. But even they will die. Larger stars live faster. Our Sun, a medium-sized yellow dwarf, will last about 10 billion years. It's currently middle-aged, about 4.6 billion years old. In another 5 billion years, its core will run out of hydrogen. No longer able to generate enough pressure to resist gravity, it will begin to collapse. The collapse will heat the core enough to fuse helium into carbon and oxygen. The star will swell into a red giant, engulfing Mercury, Venus, possibly Earth. Its outer layers will puff off into space, forming a planetary nebula. What remains will be a white dwarf, a dead star, no longer fusing anything, simply radiating away its residual heat over billions of years. And then there are the giants. Stars dozens or hundreds of times more massive than the Sun live only millions of years. They burn so ferociously that they exhaust their hydrogen in cosmic eye blinks. Then they fuse helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. Each stage releases less energy and proceeds faster than the last. Iron is the end. Iron fusion doesn't release energy, it absorbs it. When the core of a massive star turns to iron, the nuclear fires can no longer push back against gravity. The core collapses in a fraction of a second, rebounding in a supernova explosion that briefly outshines the entire galaxy. What remains depends on the mass. Stars between about 8 and 20 solar masses leave behind neutron stars, objects so dense that a teaspoon of their matter would weigh 1 billion tons on Earth. Stars above 20 solar masses collapse beyond even that threshold, crushing their cores into singularities from which not even light can escape. Black holes. All of these endpoints, white dwarfs, neutron stars, black holes, are corpses. They are remnants of stellar funeral pyres. And each one represents an enormous increase in the universe's total entropy. The ordered nuclear fuel of a star has been converted into radiation, neutrinos, and gravitational waves that disperse through space. The star's matter, once organized into fusion reactions and convection zones, is now either locked into a degenerate stellar remnant or scattered as nebula gas across light years. And this process is happening everywhere, constantly. The Milky Way alone contains somewhere between 100 and 400 billion stars. Each one is burning, converting order into chaos, marching toward its own inevitable death. Multiply that by the roughly 2 trillion galaxies in the observable universe, and you begin to grasp the scale of the entropic catastrophe we call cosmic evolution. Stars look like life. They glow, they warm, they enable existence. But they are death engines. They are accelerating the universe's slide toward equilibrium. They are beautiful, yes, achingly, impossibly beautiful, but their beauty is the beauty of a flame consuming its own wick. And every flame, eventually, goes out. For most of the 20th century, black holes were considered the ultimate containers, objects that swallowed everything and gave nothing back. Matter, light, information, all fell past the event horizon and disappeared forever. If entropy is a measure of hidden information, then black holes seem to be entropy destroyers. They erased information from the universe, lowering entropy. This bothered physicists deeply. The laws of thermodynamics, especially the second law, seemed to break down at the event horizon. Then Stephen Hawking changed everything. In 1974, combining quantum mechanics with general relativity, Hawking discovered something astonishing. Black holes are not perfectly black. At the quantum level, the violent tidal forces near the event horizon can create pairs of virtual particles, one falling into the black hole, one escaping into space. From an outside observer's perspective, the black hole is radiating particles. It has a temperature. This became known as Hawking radiation, and its implications were staggering. If black holes radiate, they lose mass. If they lose mass, They shrink. If they shrink, their temperature increases, smaller black holes radiate faster. Eventually, after an incomprehensibly long time, a black hole will evaporate completely in a final burst of radiation. Black holes are not eternal. They die. But more importantly, Hawking showed that black holes have entropy, enormous entropy. A black hole's entropy is proportional to the surface area of its event horizon, not its volume. This is encoded in the Bekenstein-Hawking formula. The entropy of a black hole equals 1/4 of its horizon area, measured in Planck units. For a supermassive black hole like the one at the center of the Milky Way, which contains roughly 4 million solar masses, the entropy is incomprehensibly large, about 10 to the power of 77 Boltzmann constants. That's more than the entropy of all the normal matter that formed it. This means black holes are not entropy destroyers, they're entropy maximizers. When matter falls into a black hole, the universe's total entropy increases dramatically. Black holes are the most efficient entropy generators in the cosmos. They take ordered matter and energy and convert it into the purest possible form of disorder, gravitational entropy encoded on a two-dimensional surface. This leads to a profound and disturbing conclusion. The final fate of matter, the ultimate high-entropy state, is not a uniform gas of particles. It's black holes. Lots of them. Given enough time, and we're talking about timescales so vast they make the current age of the universe seem like a heartbeat, gravity will pull matter together. Galaxies will merge. Stars will collide or fall into black holes. Eventually, every galaxy will collapse into a single supermassive black hole. Then, over even longer timescales measured in googolls of years, even these supermassive black holes will merge through random encounters and gravitational wave radiation. The universe will become a sparse collection of black holes, separated by ever-expanding distances, slowly evaporating through Hawking radiation. And here's where it gets truly strange. There's a paradox embedded in this process, one that has tormented physicists for 50 years. It's called the black hole information paradox. Quantum mechanics says information cannot be destroyed. It can be scrambled, hidden, transformed, but the underlying information about a system's initial state must always be preserved. But black holes, according to Hawking's original calculation, seem to destroy information. Matter falls in carrying specific quantum information. The black hole later evaporates into thermal radiation, random, featureless Hawking radiation that carries no information about what fell in. Where did the information go? Hawking originally believed it was simply destroyed, which would violate quantum mechanics. Others proposed the information was somehow encoded in the Hawking radiation through subtle correlations invisible in practice but present in principle. Still others suggested information is stored on the event horizon itself, in a holographic encoding where the three-dimensional interior is completely described by information on the two-dimensional surface. This last idea, the holographic principle, has gained significant traction and has led to revolutionary insights about the nature of space and reality itself. It suggests the universe itself might be holographic, that everything we perceive as three-dimensional might actually be information encoded on a distant two-dimensional surface. Entropy, information, and the structure of space-time appear to be far more deeply connected than anyone imagined. But the paradox remains unresolved. We don't know where the information goes. We don't fully understand what happens at the event horizon. We don't know if information is truly preserved or if quantum mechanics breaks down in the face of gravity's ultimate expression. What we do know is this: black holes are temporary. They evaporate. And when they do, they release their tremendous entropy back into the universe as a bath of featureless, thermal radiation, photons and particles with no structure, no information, no capacity to do work. They are the ultimate entropy engines, and they are running everywhere in the cosmos, slowly but inexorably, grinding the universe toward its final state. Let's talk about numbers that make infinity seem small. The current age of the universe is approximately 13.8 billion years. Written out, that's 1.38 times 10 to the power of 10 years. A comprehensible number, if barely. You could count to 1 billion if you dedicated your life to it, and then imagine that span 13 times over. Now let's move forward. In roughly 10 to the power of 12 years, 1 trillion years, the last conventional stars will die. These will be the smallest red dwarfs, having sipped their hydrogen fuel across timescales that span from the formation of the first galaxies to an era when most galaxies have faded from view. The universe will be approximately 100 times older than it is now. Still comprehensible, if you stretch your imagination. But we're just getting started. By 10 to the power of 14 years, stellar remnants, white dwarfs, neutron stars, will begin to fade to near invisibility. The universe will enter what's called the degenerate era, when the only sources of light are rare collisions or decaying orbits. Brown dwarfs, failed stars that never quite ignited fusion, will occasionally collide and briefly flare. White dwarfs will accrete matter from passing gas clouds and nova. But these events will be separated by vast gulfs of time and space. The universe will be dark, but not yet dead. At 10 to the power of 20 years, even these rare events will cease. But something else begins: orbits decay. Stars orbiting galactic centers, planets orbiting stars, moons orbiting planets, all of these are slowly losing energy through gravitational radiation, infinitesimally faint ripples in spacetime predicted by Einstein. Over 10 to the power of 20 years, this energy loss becomes significant. Stars spiral into the black holes at galactic centers. Planets fall into their stellar remnants. Structure collapses. By 10 to the power of 30 years, galaxies as we know them no longer exist. Matter has either fallen into black holes or been ejected into intergalactic space through chaotic gravitational interactions. The universe is now divided into two populations: black holes of various sizes and lonely stellar remnants scattered across exponentially expanding space. And then we wait. At 10 to the power of 36 to 10 to the power of 40 years, depending on their mass, even stable matter begins to decay. Protons and neutrons, the building blocks of atoms, are not eternal. Grand unified theories predict they should eventually decay into lighter particles through quantum tunneling. The average lifetime of a proton is estimated to be around 10 to the power of 36 years, though experiments have yet to observe a single proton decay. But if proton decay occurs, and most theories say it must, then every stellar remnant, every dead star, every fragment of rock and ice and metal scattered through the cosmos will slowly dissolve. White dwarfs will collapse into neutron stars as their protons decay away. Neutron stars will evaporate into showers of pions and gamma rays. By 10 to the power of 40 years, ordinary matter, as we understand it, no longer exists. The universe contains only black holes, subatomic particles, and radiation growing ever colder and more dilute. The black hole era has begun. Now the timescales become truly incomprehensible. Hawking radiation proceeds at a rate inversely proportional to the black hole's mass. Small black holes evaporate quickly. Stellar mass black holes formed from supernova remnants, roughly 10 solar masses, will evaporate in about 10 to the power of 67 years. That's a 1 followed by 6 to 7 zeros, a duration so long that if you started counting Planck times, the shortest possible interval, 10 to the power of -43 seconds, at the Big Bang, you wouldn't reach 10 to the power of 67 years before the entire current age of the universe had passed thousands upon thousands of times. Supermassive black holes take far longer. The black hole at the center of the Milky Way, weighing 4 million solar masses, will persist for roughly 10 to the power of 87 years. The largest black holes we've observed, ultramassive monsters containing tens of billions of solar masses, will take 10 to the power of 100 years or more to evaporate, a googol of years, a number so large it has its own name precisely because it exceeds human comprehension. But eventually, even these titans will fade. They will shrink, growing hotter as they do, radiating faster and faster, until in their final moments they explode in a burst of Hawking radiation roughly equivalent to a 1,000,000 megaton nuclear bomb. Then, nothing. By 10 to the power of 106 years, give or take a few orders of magnitude, the last black hole in the universe will have evaporated. What remains? Photons, leptons, a thin soup of particles, electrons, positrons, neutrinos, spreading ever farther apart as space expands. The temperature of the universe, already incomprehensibly cold, continues to drop. Any given particle might not encounter another particle for durations longer than all the previous eras combined. This is the dark era, the era of heat death. The universe has reached maximum entropy. There are no energy gradients left to exploit. No fusion reactions. No black holes. No stars. No structure of any kind. Just an infinite expanse of near-empty space growing colder and emptier, approaching but never quite reaching absolute zero. Time, in any meaningful sense, stops. Nothing changes. Nothing can change. The universe has reached thermodynamic equilibrium, the state from which the second law says it can never escape. This is not the end. The universe continues existing. Particles continue existing. Quantum fields continue existing. But nothing happens. No complexity. No structure. No life. No thought. No meaning. Just silence. Eternal, absolute silence. The mathematics are clear. The physics are settled. Given our best understanding of the laws of nature, this is the inevitable fate of everything. Not today, not tomorrow, not for trillions of years. But eventually, inevitably, 100 trillion years from now, a duration so long that the entire history of humanity, from the first upright ape to the last transmitted signal, will be a rounding error, a quantum fluctuation, a brief fever dream in the universe's long memory. The stars are gone. All of them. the brilliant blue giants that once outshone millions of suns. The countless yellow dwarfs like our own sun, steady and life-giving. Even the dim red embers, those patient misers of hydrogen, have finally exhausted their fuel. The last star flickered out tens of trillions of years ago. Its death went unnoticed. There was no one left to notice. What remains? White dwarfs. Billions upon billions of them scattered through the expanding darkness, the cooling corpses of stars like our Sun. They're roughly Earth-sized, yet contain as much mass as the Sun, matter compressed so tightly that electrons are smashed together in a degenerate state, held apart only by quantum mechanical pressure. They glow faintly with residual heat, radiating away the warmth accumulated during their former lives as nuclear furnaces. Over tens of trillions of years, they've cooled from hundreds of thousands of degrees to thousands, then hundreds, then mere tens of degrees above absolute zero. They are called black dwarfs now, though this is a misnomer. They're not black holes, and they're no longer dwarf stars. They're crystallized spheres of carbon and oxygen, diamond-like objects floating in the void, invisible except for the faintest infrared glow. Neutron stars, too, remain. The collapsed cores of massive stars, objects so dense that a sugar cube of their matter would weigh as much as a mountain. They've stopped spinning. Their magnetic fields, once powerful enough to create pulsar beams visible across galaxies, have decayed. They sit silent in the darkness, occasionally disturbed when a brown dwarf or planet or fragment of ancient debris spirals into them, adding infinitesimally to their mass. Brown dwarfs, failed stars that never accumulated enough mass to ignite fusion, drift through space, cooling like the white dwarfs but never having burned at all. They're massive Jupiters, gas giants that almost made it to starhood, now frozen husks radiating faint heat into a universe that has grown colder than they are. And everywhere, threading through this darkness, are planets. Rocky worlds and gas giants, orphaned when their stars died, now wandering alone through intergalactic space. Most were ejected from their solar systems during the chaotic death throes of their stars or in gravitational interactions with other stellar remnants. They're frozen solid, their atmospheres collapsed into ice and snow on their surfaces, nitrogen ice, oxygen ice, even hydrogen and helium ices at temperatures just a few degrees above absolute zero. Earth might be among them. If it survived the Sun's red giant phase, unlikely but possible, it would have been flung into space billions of years ago, carrying with it the frozen remnants of its oceans, the fossilized traces of everything that once lived, entombed in ice and darkness. Nothing moves quickly in this era. Without stars, without fusion, without any nearby source of energy, the only processes that occur are those driven by quantum mechanics and gravity, operating over timescales that make geological epochs seem like camera flashes. Occasionally, once every trillion years, perhaps, in any given region of space, two brown dwarfs collide. The impact generates heat, briefly raising the temperature enough for fusion to occur. For a few thousand years, there is light. A faint red glow, barely enough to illuminate the two merging objects. Then it fades, and darkness returns. Even more rarely, a black or white dwarf might accrete enough matter from a passing gas cloud, the diffuse remnants of ancient nebulae, to reignite fusion in a nova explosion. These events, once common in the stellar era, now occur so infrequently and in locations so scattered that the universe could exist for quadrillions of years between successive novae. But the dominant process in this era is not creation. It's decay. Orbits are not eternal. Every object in orbit around another, planets around stellar remnants around galactic black holes, is slowly losing energy through gravitational radiation. Einstein's general relativity predicts this. Accelerating masses emit gravitational waves, infinitesimally weak ripples in spacetime that carry energy away from the system. For typical planetary orbits, this process is negligible on human or even stellar timescales. Earth loses about 10 to the power of -29 watts to gravitational waves, less energy than a single atom radiates as heat. At this rate, it would take longer than the current age of the universe for Earth's orbit to decay noticeably. But over 10 to the power of 20 years. Gravitational radiation becomes the dominant force. Orbits spiral inward. Planets fall into their dead stars. Stellar remnants fall into the black holes at galactic centers. Binary stars, pairs of white dwarfs or neutron stars orbiting each other, spiral together and merge in final catastrophic collisions. Each collision releases a burst of energy, gravitational waves, neutrinos, electromagnetic radiation, that propagates through space at light speed, illuminating nothing because there is nothing to illuminate. The energy disperses, spreads, becomes part of the ever-cooling background radiation. Entropy increases. By the end of the degenerate era, around 10 to the power of 40 years, the universe has undergone a profound simplification. Galaxies no longer exist as coherent structures. Most matter has either fallen into black holes or been ejected into intergalactic space through gravitational slingshots. What remains of stellar remnants is scattered across distances so vast that each object is effectively alone in its own pocket universe, separated from its nearest neighbor by billions of light-years. The temperature of space itself, the cosmic microwave background, now stretched by expansion into radio waves and beyond, has cooled to 10 to the power of -13 Kelvin. 1/10 of a degree above absolute zero. At this temperature, quantum effects dominate. Virtual particles flicker in and out of existence. The vacuum itself undergoes minute fluctuations. But there is no one to observe them. No life. No consciousness. Just dead matter drifting through the expanding void, waiting for the next era to begin. The era of black holes. 10 to the power of 40 years have passed. Protons have decayed. Ordinary matter, as we knew it, no longer exists. What remains are black holes. And they are alone. Black holes of every size, scattered across the universe at distances that grow larger with each passing eon. Stellar mass black holes, the remnants of ancient supernovae, containing 10 to 100 times the mass of the original Sun. Intermediate black holes, formed from the collision and merger of countless stars in the dense cores of long-dead globular clusters. Supermassive and ultramassive black holes, the seeds around which galaxies once formed, now containing millions or billions of solar masses. They are the last macroscopic structures in the universe. They are not alive, nothing is alive, but they are, in a certain sense, the final heirs to all that came before. Every star that burned, every planet that formed, every life that ever existed has ultimately contributed its mass to these gravitational wells. They are the monuments, the tombstones, the final word. And they are evaporating. Stephen Hawking showed that black holes radiate, but the radiation is staggeringly slow for large masses. A stellar mass black hole of 10 solar masses radiates at a temperature of about 6 billionths of a Kelvin, far colder than the cosmic background radiation was even in the degenerate era. It emits perhaps one photon every few years, each photon carrying away an infinitesimal amount of mass energy. At this rate, it will take roughly 10 to the power of 67 years for such a black hole to completely evaporate. That's 10 million trillion 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 years. Written out, 10 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 years. Your mind cannot hold this number. No human mind can. It is not merely large, it is larger than large in a way that breaks comprehension. If you had begun counting at the Big Bang, one number per Planck time, the smallest possible duration, you would still be counting when the universe reaches 10 to the power of 67 years. But the universe has time. Infinite time, perhaps. And so it waits. The black holes radiate. Slowly, immeasurably slowly, they shrink. As they shrink, their temperature increases, inversely proportional to their mass. A black hole half the size is twice as hot. And hotter black holes radiate faster. This creates a runaway process. The smaller the black hole, the faster it evaporates. The faster it evaporates, the smaller it gets. In the final moments of a stellar mass black hole's life, after 10 to the power of 67 years of slow decline, it suddenly, relatively speaking, explodes. Its temperature spikes to billions of degrees. It radiates gamma rays, particle-antiparticle pairs, a final defiant burst of energy equivalent to millions of nuclear weapons. Then, nothing. The black hole is gone. In its place is an expanding shell of radiation, already diluting into the void, already cooling, already becoming indistinguishable from the background. One more voice in the silence. Supermassive black holes take far longer. The monster at the center of the Milky Way, containing roughly 4 million solar masses, will persist for about 10 to the power of 87 years. The largest black holes we've observed, ultramassive behemoths containing tens of billions of solar masses, might last 10 to the power of 100 years or beyond. A googol of years. The number is so large that it has ceased to represent time in any meaningful sense. Cause and effect become statistical abstractions. The very concept of happening loses coherence. And yet, the black holes continue to exist. They continue to radiate. Hawking radiation is not optional, it's a consequence of quantum mechanics operating at the event horizon. Vacuum fluctuations create particle-antiparticle pairs. One falls into the black hole, one escapes. To an outside observer, the black hole has emitted a particle. It has shrunk. This process is not smooth. Hawking radiation is thermal, random. The black hole emits particles in all directions, at all energies permitted by its temperature. There's no structure, no information, just featureless heat. Or is there? The information paradox haunts this era. If black holes destroy information, then quantum mechanics is violated. If they preserve information, then where is it encoded? Some proposals suggest the information is released in subtle correlations in the Hawking radiation, patterns too fine to detect with any conceivable instrument, but present nonetheless. Others suggest information is never inside the black hole at all, but is holographically encoded on the event horizon, a two-dimensional surface containing all the data about the three-dimensional interior. These are not just academic questions. They go to the heart of what reality is. Is information fundamental? Is space-time emergent from quantum information? Are we living in a hologram, a projection from a distant boundary? The black holes, radiating silently into the void, offer no answers. They simply continue their slow dissolution, converting their mass into entropy, fulfilling the second law's mandate with glacial inevitability. As the black hole era progresses toward its end, the universe becomes ever more sparse. Black holes evaporate one by one, starting with the smallest and ending with the largest. The radiation they emit spreads outward at light speed, diluting into the exponentially expanding space. The temperature of this radiation, once fierce, cools as it expands, redshifting through the electromagnetic spectrum and beyond, until it becomes indistinguishable from the vacuum fluctuations of empty space. By 10 to the power of 106 years, give or take a few orders of magnitude depending on the masses of the largest black holes, the last black hole evaporates. There is a final burst of radiation, weak, almost gentle, scarcely brighter than the quantum foam, and then it's gone. The universe contains no macroscopic structures, no stars, no planets, no black holes, only particles, photons, leptons, neutrinos, scattered across distances so vast that each might as well be alone in its own universe. The dark era has begun, and with it, the final state. Heat death. This is the end of the story. Not because the universe ceases to exist, but because nothing can happen anymore. We are now beyond 10 to the power of 100 years. A googol of years. A duration so far beyond human comprehension that all metaphors fail. If every atom in the observable universe were itself a universe, and every atom in those universes were again a universe, and you counted all the atoms in all those nested universes, you would still fall short of a googol. The universe has reached maximum entropy. Thermodynamic equilibrium. The state from which the second law says there is no escape. What does this look like? Space continues to expand, following the accelerating expansion driven by dark energy or the cosmological constant. The rate of expansion is now so extreme that distant particles are receding from each other faster than light, not because they're moving through space faster than light, but because space itself is stretching between them. Each particle, photon, electron, positron, neutrino, occupies its own causally disconnected region. Its horizon, the sphere beyond which no light or information can ever reach it, contains only vacuum. If two particles were initially close, they are separated now by distances measured in googolplexes of light years. They will never interact again. The temperature of the universe is incomprehensibly cold. If the cosmic microwave background was at 2.7 Kelvin in our era, and it is cooled by a factor of the universe's expansion, then by 10 to the power of 100 years it has cooled to something like 10 to the power of negative 100 Kelvin or lower. At this temperature, even virtual particles barely flicker into existence. The vacuum is as still as the laws of quantum mechanics permit. There are no energy gradients, no hot regions and cold regions, no dense regions and sparse regions. Everything is uniform, spread evenly by expansion and entropy. And without energy gradients, no work can be done. No processes can occur. No complexity can form. Time, in the sense of change, has effectively stopped. Oh, the universe continues to exist. Quantum fields permeate space. Particles still have properties: mass, charge, spin. The laws of physics still operate. But nothing distinguishes one moment from the next. If you could somehow observe the universe in this era, and then observe it again after a googol years more, you would see no difference. Nothing would have changed because nothing can change. This is heat death. Not fire, not ice, but uniformity. The ultimate democratic principle: everything has become the same. Every location in space is indistinguishable from every other location. Every moment in time is indistinguishable from every other moment. Entropy has reached its maximum value. The universe has spent all its usable energy. The arrow of time, which has pointed steadily toward increasing entropy for over 10 to the power of 100 years, has hit its target. There is nowhere left for it to point. And yet, quantum mechanics refuses absolute stillness. Even in this dead universe, vacuum fluctuations continue. Virtual particles appear in pairs, exist for Planck time durations, and annihilate. These fluctuations are tiny, unimaginably tiny, but they're non-zero. And given infinite time, even the most improbable fluctuations will eventually occur. A proton might spontaneously appear, or two protons, or a hydrogen atom. These are fantastically unlikely. The probability is 1 divided by an exponential so large it would require scientific notation to even write the exponent. But probability is not zero. Given enough time, and enough time here means timescales that make 10 to the power of 100 years look like a sneeze, larger fluctuations become possible. A cubic centimeter of matter, a star, a solar system, a brain. This is the return of Boltzmann's nightmare. In a universe at maximum entropy, given infinite time, random quantum fluctuations will eventually assemble complex structures by pure chance. The most probable complex structure capable of having experiences is not an entire universe with consistent physics and history. It's a single brain, momentarily fluctuated into existence, complete with false memories of a past that never happened and observations of a world that doesn't exist. A Boltzmann brain. If the universe exists at equilibrium for infinite time, then Boltzmann brains will vastly outnumber real observers who evolved in low entropy conditions. Statistically, if you are an observer, you are far more likely to be a Boltzmann brain than a human being who evolved on Earth. Your memories are lies. Your observations are hallucinations. You will dissolve back into the void within seconds. And this horror of solipsism and unreality is the logical conclusion of Boltzmann's statistical mechanics applied to an eternal equilibrium universe. Unless Unless the universe is not eternal, unless the heat death is not truly final, unless there are exceptions, loopholes, escape clauses written into the laws of physics that we haven't yet discovered. If entropy is inevitable, if the heat death of the universe is certain, then is there any possible way for consciousness, for thought, for experience, for meaning, to persist? Some have tried to imagine it. In 1979, physicist Freeman Dyson published a paper titled Time Without End, exploring whether life could survive indefinitely in an expanding, cooling universe. His conclusion was cautiously optimistic, but only under very specific conditions. Dyson reasoned that life is, fundamentally, information processing. A thinking being must process information, and information processing requires energy. But it also generates heat, and that heat must be radiated away to prevent the system from overheating. In a universe growing ever colder, the rate at which you can radiate heat decreases, which means the rate at which you can think also decreases. But decreasing is not the same as stopping. Dyson proposed that an advanced civilization might adapt to the cooling universe by slowing its metabolism. Think for a while, then hibernate for much longer while to radiate waste heat, then wake and think again. As the universe cools, the thinking periods become shorter and the hibernation periods become longer, but the ratio could be adjusted such that the total number of thoughts, the integrated subjective experience, approaches infinity, even as the objective time stretches to infinity. It's a beautiful idea. A civilization that learns to think slower and slower, stretching each thought across eons, but never stopping, never ending, experiencing infinite subjective time within finite energy. But there are problems. First, Dyson's calculation assumed the universe would expand forever but not accelerate. We now know the expansion is accelerating due to dark energy. This changes everything. In an accelerating universe, horizons form, causal boundaries beyond which no information can ever reach you. Resources become limited in principle, not just in practice. You're confined to a shrinking bubble of accessible space as distant matter accelerates away beyond your horizon. Second, Dyson assumed matter is stable. But if protons decay, then your substrate, the physical stuff you're made of, eventually crumbles. You'd have to transfer yourself into more stable forms, from atoms to radiation, perhaps, or into patterns in electromagnetic fields. But these are increasingly diffuse, increasingly fragile. At some point, the definition of you becomes so spread out, so diluted, that it's unclear whether you still exist as a coherent entity. Third, and most fundamentally, Dyson's scheme requires reversible computing, computation that generates no entropy, no waste heat. Such computation is theoretically possible according to Landor's principle, which states that only the erasure of information requires energy. If you never erase anything, never discard memories or intermediate calculations, you can in principle compute without generating heat. But perfect reversible computing might be impossible in practice. Quantum mechanics introduces fundamental randomness. Interactions with the environment cause decoherence. And even if you could build a perfect reversible computer, you'd need to store every bit of every calculation forever. Your memory requirements would grow without bound, eventually requiring more mass energy than exists in your causally connected region. So Dyson's optimism, while inspiring, likely doesn't survive detailed scrutiny. Others have proposed even more speculative scenarios. Perhaps advanced civilizations could migrate toward black holes, using their gravitational energy to power computation. Black holes create extreme time dilation. Time runs slower near the event horizon, as seen from outside. A civilization falling toward a black hole could experience subjective eons while only moments pass externally. But black holes evaporate. And when they do, everything near them is bathed in Hawking radiation. There's no permanent refuge. Another proposal: if cosmic topology is more complex than we think, if the universe has wormholes or closed time-like curves or exists in higher dimensions, then perhaps there are escape routes. Passages to younger universes, pockets of low entropy, regions where the second law hasn't yet completed its work. But these are purely speculative. We have no evidence for such structures, and most violate causality or energy conservation in ways that seem incompatible with known physics. The truth is, consciousness appears to require disequilibrium. Thought requires energy flow, structure, gradients. In a maximum entropy universe, none of these exist. The heat death is not just the death of stars and galaxies, but the death of the very possibility of experience. Unless consciousness is more fundamental than we think. Some interpretations of quantum mechanics suggest observation plays a constitutive role in reality. The universe collapses into definite states only when observed. If consciousness is somehow woven into the quantum fabric itself, then perhaps it persists in forms we can't currently imagine: ghostly quantum processes in the vacuum fluctuations, patterns in the quantum foam, subjective experiences divorced from material substrate. But this is philosophy, not physics. It's a hope, not a prediction. The brutal reality remains: all known forms of complexity, including consciousness, require low entropy. The universe began with low entropy, and that reservoir is being depleted. When it's gone, consciousness, at least as we understand it, will be impossible. We are candles burning against an infinite night. And when our fuel is spent, the darkness is absolute. Imagine you wake up. You have memories, childhood, education, relationships, experiences. You look around and see a room, a world, a universe that seems consistent with those memories. You have every reason to believe you are a real person with a real history in a real cosmos. But statistically, you are almost certainly not. This is the Boltzmann brain paradox, and it represents one of the deepest and most disturbing problems in cosmology and the philosophy of science. Here's the logic: if the universe eventually reaches maximum entropy and remains at that state for infinite time, then quantum fluctuations will occasionally produce ordered structures by pure chance. The probability of any given fluctuation is extraordinarily small, but with infinite time, even the improbable becomes inevitable, and in fact happens infinitely many times. Now, what's the most probable fluctuation that could produce an observer, a conscious entity capable of having experiences? You might think it's a universe like ours: 13 billion years of cosmic evolution, galaxies forming, stars igniting, planets coalescing, life emerging, intelligence evolving. But this is an enormously complex, low-entropy state. The probability of such a universe fluctuating into existence is incomprehensibly small. Far more probable is a much smaller fluctuation, just a single brain popping into existence complete with false memories of that entire history. From the brain's subjective perspective, it would be indistinguishable from a real person with a real past. But objectively, it would be a momentary random assembly of particles floating in the void, doomed to dissipate back into chaos within seconds. And here's the horrifying part. If the universe spends infinite time at maximum entropy, the number of Boltzmann brains vastly exceeds the number of real observers who evolved through normal processes. If you select an observer at random from all possible observers across infinite time, you're far more likely to pick a Boltzmann brain than a real human. So, statistically, you are probably a Boltzmann brain. Your memories are false. Your observations are hallucinations. You are a ghost, a statistical fluke, and you will cease to exist in moments. Of course, you don't believe this. It seems absurd, solipsistic, paranoid. But how can you refute it? Any evidence you might gather, scientific measurements, historical records, other people confirming your memories, could itself be part of the false memories fluctuated into your brain. There is no empirical test that could distinguish between real observer in a low-entropy universe and Boltzmann brain with false memories. This paradox tormented Boltzmann himself. He proposed it as a thought experiment to show how unlikely fluctuations could produce observers in an equilibrium universe. But the logic turned against him. If his statistical mechanics was correct, then most observers should be Boltzmann brains, which means we should not observe the ordered, low-entropy universe we do observe. The fact that we observe stars and galaxies and consistent histories is evidence against the very theory Boltzmann was proposing. He never resolved this paradox. It haunted him, contributing to the intellectual despair that may have led to his suicide. Modern cosmologists have tried to escape the paradox through various means. One approach is to argue that the universe won't remain at equilibrium forever. Perhaps it ends, or cycles, or has a finite lifetime for some other reason. If the total time is finite, then Boltzmann brains remain vastly improbable and real observers dominate. Another approach invokes the anthropic principle. We necessarily find ourselves in a part of the multiverse capable of supporting real observers, even if Boltzmann brains dominate most regions. This doesn't solve the paradox so much as exclude ourselves from it by definition. A third approach questions whether Boltzmann brains are actually conscious. Perhaps false memories aren't the same as real memories in some crucial way. Perhaps consciousness requires continuity, or embeddedness in a real causal history, or something else that random fluctuations can't provide. But this is speculative. We don't understand consciousness well enough to say. The most radical solution is to abandon the idea that the universe reaches equilibrium and stays there forever. Perhaps entropy has a maximum, and when it's reached, something else happens: a quantum bounce, a phase transition, a creation of new space-time. The universe might be cyclic, eternally dying and rebirthing, never settling into permanent equilibrium. But we don't know. And until we do, the Boltzmann brain paradox remains a dark shadow over our understanding of cosmic evolution. It forces us to confront an uncomfortable truth. The same statistical mechanics that explains why coffee cools and why entropy increases also implies, if taken to its logical conclusion, that your existence is probably an illusion. The laws that govern reality seem to undermine the reality of everything those laws describe. Perhaps this is the ultimate entropy, not the heat death of matter and energy, but the heat death of meaning itself. The dissolution of truth into probability, of experience into statistics, of reality into quantum foam. You are probably not a Boltzmann brain. Probably. The universe probably did begin in a low entropy state and probably did evolve through natural processes to produce real observers like you. But the fact that probably is the strongest statement we can make should terrify you. Because it means entropy doesn't just destroy stars and galaxies. It destroys certainty itself. But what if we're wrong? What if the heat death, for all its mathematical inevitability, is not the final word? Science progresses by questioning assumptions, finding loopholes, discovering that what seemed certain was merely contingent. Newton's mechanics, thought to be absolute, gave way to Einstein's relativity. Classical determinism gave way to quantum uncertainty. Perhaps the heat death, too, has exceptions. Consider eternal inflation. This theory proposes that the Big Bang wasn't a singular event but part of an endless process. Quantum fluctuations in a primordial inflating spacetime spawned bubble universes like ours, each with its own Big Bang, its own laws of physics, its own destiny. Our universe might be dying toward heat death, but the multiverse is eternally creating new universes, new pockets of low entropy, new beginnings. If true, this means the cosmos as a whole never reaches equilibrium. It remains eternally far from maximum entropy, constantly birthing new structure even as old universes die. Death is local, but creation is eternal. But there's a problem: we're trapped in our bubble. The space between universes is inflating faster than light. We can never reach another universe, never escape our own heat death, never access the eternally renewed multiverse beyond our horizon. It continues, perhaps, but without us. Another possibility: cyclic cosmology. What if the universe doesn't expand forever? What if dark energy isn't constant but changes over time, eventually reversing into an attractive force that pulls the universe back together? Then expansion would slow, stop, and reverse. The universe would collapse back into a big crunch, possibly rebounding into a new Big Bang. This would be a cosmic phoenix, dying and resurrecting eternally. Each cycle would erase the previous one. No information would survive the crunch, but the cosmos itself would be immortal, never reaching permanent equilibrium because equilibrium would be interrupted by collapse and renewal. The evidence, however, doesn't favor this. Dark energy appears to be the cosmological constant, a property of spacetime itself, unchanging and eternal. If so, the universe will expand forever, accelerating forever, never collapsing. Unless we've misunderstood something fundamental. Some theories suggest spacetime itself is unstable. The vacuum we exist in might be a false vacuum, a metastable state that could spontaneously decay into a lower energy true vacuum. If this happens, a bubble of true vacuum would form and expand at light speed, converting everything it touches. The laws of physics might be different in the true vacuum. Particles might have different masses, forces might have different strengths. Our universe would be destroyed, replaced by something alien. This is called vacuum decay, and it's one of the few scenarios that could end the universe faster than heat death. If it occurs, we wouldn't see it coming. The bubble wall would approach at light speed, meaning the first sign would be our instantaneous annihilation. The probability of vacuum decay is unknown. It could happen in the next second, or it might take 10⁻⁴ years, or it might never happen at all. We simply don't know enough about quantum field theory at high energies to calculate the probability. But if it does happen, heat death becomes irrelevant. The universe doesn't die slowly through entropy, it dies suddenly, violently, in a phase transition that resets everything. Then there's the question of proton decay. I mentioned earlier that protons are predicted to decay after roughly 10⁻36 years, dissolving atoms and stellar remnants. But we've never observed a proton decay. Experiments have placed lower bounds on the proton lifetime, but they haven't confirmed that protons decay at all. What if they don't? If protons are truly stable, then matter persists indefinitely. White dwarfs, neutron stars, even solitary protons floating in the void would remain, unchanged, forever. The black hole era would still occur, black holes would still evaporate, but afterward, the universe would contain stable particles, not just radiation. This might create possibilities for structure we haven't considered. Perhaps, given unimaginable stretches of time, matter could reorganize through gravitational interactions or quantum tunneling into new configurations. It's a fragile hope, but it's not zero. Another heretical thought: what if entropy doesn't always increase? The second law of thermodynamics is statistical, not absolute. For a small system, fluctuations can temporarily decrease entropy. We see this in biological systems all the time. Local order increases at the expense of greater global disorder. But what about for the universe as a whole? Most physicists would say the second law applies universally, that the universe's total entropy can only increase. But this assumes the universe is a closed system. What if it's not? What if there's an external reservoir, a larger context, a higher dimensional structure that allows energy or information to flow in or out? Then the second law might not apply in its simple form. This is wildly speculative. We have no evidence for anything outside our universe, no way to test such hypotheses. But the point is, our understanding is incomplete. The laws we know might be approximations, valid in our local region of space-time, but breaking down under conditions we can't yet access. The heat death is the prediction of our best current theories. But theories change. Newton's deterministic universe gave way to quantum probability. Maybe thermodynamics, too, has a deeper layer we haven't yet discovered. Or maybe not. Maybe the universe really is dying, slowly and irreversibly, toward a final equilibrium from which there is no escape. Maybe all these alternatives are desperate fantasies, refusals to accept the evidence. But hope, too, is a form of rebellion against entropy. And as long as consciousness exists, hope will persist. Even if it's irrational. Even if it's doomed. Even if it's simply part of the dream of a Boltzmann brain dissipating into the void. Why did the universe begin with low entropy? This is not a rhetorical question. It's arguably the deepest unsolved problem in cosmology. The second law of thermodynamics says entropy increases, but it doesn't explain why entropy started low. And low is an understatement. The early universe was in a state of such improbable order that if you randomly selected a universe configuration from all possible configurations, the probability of getting something like our early universe is 1 divided by a number so large it makes a googolplex look like a rounding error. Penrose calculated this probability, roughly 1 in 10 caret 10 caret 123. Written out, that's 1 in 10 to the power of 10 to the power of 123. A number so vast that there aren't enough particles in the observable universe to represent its digits. Why would the universe start in such a special state? One answer: it just did. Initial conditions are boundary conditions, not things physics explains. You specify them and then calculate forward. If someone asks why those initial conditions and not others, you shrug and say, that's what happened. This is unsatisfying but not necessarily wrong. Physics describes how systems evolve, not why they started the way they did. Asking why the universe began with low entropy might be like asking why it has 3 spatial dimensions or why electrons have the mass they do. It's a fact about our universe, and facts don't always have explanations. But there's another option, the anthropic principle. Imagine a multiverse, an ensemble of universes with all possible initial conditions. Most of these universes start in high entropy states and stay there. No structure forms, no stars, no planets, no life, no observers. A tiny fraction of universes start in low entropy states. These universes can evolve complex structures. Life can emerge. Observers can ask questions. We necessarily find ourselves in one of the rare low-entropy universes because those are the only universes capable of producing us. It's a selection effect. The vast majority of universes are sterile, but we don't observe them because there's no one there to observe. This is called the weak anthropic principle, and it's fairly uncontroversial. Of course we observe conditions compatible with our existence. How could it be otherwise? But there's a stronger version. Perhaps the universe's initial conditions are not just compatible with observers but somehow selected or required by the fact that observers exist. This veers into controversial territory, suggesting that consciousness plays a fundamental role in shaping reality. Most physicists are uncomfortable with this. It smells of teleology, of purpose, of intelligence design. Science has spent centuries exorcising purpose from nature. Planets don't orbit because they want to. Evolution doesn't happen to produce humans. Reintroducing observer dependence at a cosmological level feels like a step backward. Yet quantum mechanics already suggests observers matter. The act of measurement collapses wave functions, determining outcomes that were previously in superposition. Extend this to cosmology. Perhaps the universe's wave function includes all possible histories, all possible initial conditions, and the act of observation selects the branch we find ourselves in. This is deeply speculative, bordering on metaphysical. But the low entropy problem is so severe that some physicists take it seriously. Another approach: maybe the low entropy isn't special. Maybe it's an inevitable feature of quantum gravity or a creation event. The Big Bang might emerge from a quantum fluctuation in a pre-existing spacetime, and the laws governing such fluctuations might naturally produce low-entropy beginnings. Or perhaps our universe is part of a cycle. Maybe it emerged from the collapse of a previous universe, inheriting low entropy from the dynamics of the bounce. Each cycle resets the entropy clock, allowing structure to form again. But none of these explanations are confirmed. They're hypotheses, speculations, mathematical possibilities. The truth is, we don't know why the universe started with low entropy. And without knowing that, we don't fully understand the most fundamental fact about our existence: why there is order instead of chaos, structure instead of void, stars instead of silence. The anthropic principle offers a kind of answer. We're here because we can only be here in a universe like this. But it's an answer that explains by not explaining, that resolves the mystery by making it a tautology. Perhaps that's all we'll ever have. Perhaps the question why low entropy is unanswerable in the same way why does anything exist is unanswerable, a boundary of knowledge beyond which only philosophy and speculation can venture. But the question haunts cosmology, because if we can't explain why the universe started in a low entropy state, then we can't fully justify our belief that it will end in a high entropy one. The heat death is a prediction based on extrapolating the second law forward. But if the initial conditions are miraculous or anthropically selected, who's to say the final conditions aren't equally special? Maybe there's a mechanism we don't understand that resets entropy. Maybe the universe is far stranger and more resilient than our equations suggest. Or maybe, probably, the heat death is real, inevitable, and ultimate. The low entropy beginning was a cosmic accident, a quantum fluctuation, a one-time gift that allowed structure to briefly flourish before the universe returns to its natural state, equilibrium. We are the flame that briefly illuminates the darkness. And when we ask why the flame exists, the universe offers no answer. Only the flame itself, burning, and the knowledge that it will not burn forever. Let's conduct a thought experiment. Imagine you're the last conscious being in the universe. The last star died eons ago. The last black hole evaporated millennia past. You exist as some improbable construct, perhaps an AI running on the energy of vacuum fluctuations, or a Boltzmann brain's final coherent moment. Around you is nothing but cold, empty space stretching to infinity. You think one last thought. Then you cease. What has been lost? On one level, the answer is obvious. You have been lost. Your experiences, memories, thoughts, all the qualia that made you you, have dissipated into the void. Subjective experience has ended. Consciousness, at least in this region of space-time, is gone. But on a deeper level, the question becomes strange. Information about you, every particle position, every quantum state, still exists, in principle, encoded in the universe's configuration. The universe is deterministic, or quantum mechanically probabilistic, which is deterministic in terms of the wave function. Nothing is truly destroyed, it's just scrambled beyond recovery. But is it? Hawking radiation is thermal, random, carrying no information about what formed it. If black holes destroy information, then perhaps information can be destroyed. And if information can be destroyed, then perhaps meaning can be destroyed. Not just hidden or scrambled, but genuinely, ontologically erased from existence. This would be a violation of unitarity, one of the most fundamental principles in quantum mechanics. Unitarity says total probability is conserved, that information about a system's initial state is preserved in its evolution. If unitarity is violated, then the past doesn't determine the future, and physics as we understand it breaks down. Most physicists believe information is preserved, even through black hole evaporation. But how? Where is it encoded? How does it escape? These questions remain unsolved. If information is preserved, then in principle, even after heat death, the universe retains a complete record of everything that ever happened, every thought, every action, every photon that ever propagated. It's just encoded in such a dispersed, inaccessible form that no observer could ever reconstruct it. The information exists, but it's meaningless because there's no one to interpret it. Is that different from not existing? This touches on deep questions in philosophy of mind and metaphysics. Does a mind exist if there's no one experiencing it? Does a memory exist if it can never be recalled? Does history exist if there are no historians? One view: experience is fundamental. Consciousness, qualia, subjective awareness, these are primitive features of reality, irreducible to physical processes. If this is true, then when consciousness ends, something genuinely ontological is lost. The universe doesn't just lose complex structures, it loses the capacity for anything to matter, for anything to be felt or known or cared about. Another view: consciousness is emergent, a property of certain physical configurations. When those configurations dissipate, consciousness ends, but nothing fundamental is lost, just one particular arrangement of matter energy. The universe continues, indifferent. A third view: consciousness is information processing, and the information is never lost. Even in heat death, even in maximum entropy, the information about every conscious experience still exists, encoded in the correlations between particles, the phases of quantum fields, the holographic boundary of the universe. In this view, nothing truly dies. It just becomes inaccessible. But accessibility might be essential. If a tree falls in a forest and no one can ever know it fell, did it fall? If information exists but can never be decoded, does it exist in any meaningful sense? When the last observer disappears, the universe loses more than complexity or structure. It loses witness. There is no longer anyone to observe the cosmic microwave background, to measure the positions of particles, to collapse wave functions. Some interpretations of quantum mechanics suggest observation is constitutive. The universe doesn't have definite properties until observed. If true, then when observation ends, reality itself might become indeterminate, a ghost universe of uncollapsed possibilities. This is philosophy, not physics. But physics alone can't tell us what matters. It can describe particles and fields and their evolution, but it can't tell us why any of it should be valued, why existence is better than non-existence, why consciousness matters. And yet, we act as if it does matter. We act as if experiences are real, as if beauty and love and knowledge have intrinsic value. We resist entropy not because we think we'll win, but because resistance itself seems meaningful. When everything dies, when the last structure dissolves, the last particle loses connection with all others, the last quantum fluctuation fades, what is lost is not just physical complexity. It's the capacity for anything to mean anything. The heat death is not just the death of matter and energy. It's the death of meaning, purpose, value. Not because these things are destroyed in any physical sense, but because there's no one left to instantiate them, to care about them, to fight for them. The universe becomes, in some fundamental sense, over. Not gone, but finished. A story with no readers, a song with no listeners, an equation with no mathematicians. And perhaps that's the most profound loss of all. Not that things cease to exist, but that they cease to matter. So here we are, you and I, together in this moment, contemplating the end of everything. The universe is 13.8 billion years old. It will take 10 to the power of 100 years, a Google, to reach heat death. We are, quite literally, at the very beginning. If the universe's lifetime were compressed to a single year, the current moment would be less than 1 second after midnight on January 1st. Human civilization would be a fraction of a nanosecond. Your life, incomprehensibly brief. And yet, here you are, conscious, aware, capable of understanding that you are a temporary structure in an entropic universe, a brief flame in an eternal night. This should be terrifying. And perhaps it is. But consider what it means. You are impossible. Not literally, obviously you exist, but statistically. The probability that this particular arrangement of particles that comprises you should exist, should be alive, should be conscious, should be contemplating the heat death of the universe, is so infinitesimally small that it might as well be zero. And yet here you are, a local, temporary violation of the universe's slide toward equilibrium. You are made of atoms forged in ancient stars. Carbon, oxygen, nitrogen, these elements didn't exist in the early universe. They were created through stellar nucleosynthesis, cooked in the cores of stars that lived and died before the sun was born. When those stars exploded, they scattered these elements across space. They became part of the nebula that collapsed to form our solar system. They condensed into Earth. They were incorporated into early life. They evolved. Eventually, through billions of years of entropy-increasing processes, they assembled into you. You are stardust contemplating stars. You are the universe become self-aware. And not just aware, but capable of understanding its own fate. You can grasp, intellectually if not emotionally, that the stars will die, the galaxies will fade, the black holes will evaporate, and silence will reign forever. No other structure in the known universe has this capacity. Not stars, not galaxies, not even other forms of life, as far as we know. Only you. Only us. Only minds. This is not a consolation against entropy. Entropy doesn't care about your awareness. The heat death will come regardless of whether anyone understands it or laments it or fights against it. The second law is not impressed by consciousness. But perhaps meaning doesn't require permanence. Perhaps value doesn't require eternity. Consider a symphony. Beethoven's Ninth, say, or whichever piece moves you most deeply. It exists in time. It has a beginning, a middle, an end. When it ends, it's over. The sound waves disperse. The information is lost. If you don't record it, future generations will never hear that specific performance. It's gone. Does this make it meaningless? Does its transience negate its beauty? Of course not. The symphony is meaningful precisely because it unfolds in time, because each note leads to the next, because tension resolves to harmony. If it lasted forever, unchanging, it would cease to be music. It would be noise, or silence, or perhaps something beyond description, but certainly not art. The same is true of life, of consciousness, of civilizations and stars and universes. Meaning exists in the unfolding, not in the permanent. Beauty requires transience. Structure requires the contrast between order and entropy. You might object, but a symphony ends after minutes or hours, and people remember it. The universe's heat-death leaves no one to remember anything. The entire cosmic story will be erased, not just forgotten but ontologically obliterated. True. And yet, this doesn't make the story meaningless now. Right now, in this moment, you are experiencing something. You're reading words, thinking thoughts, feeling feelings. These experiences are real. They have texture, depth, qualia. The fact that they will end, that you will end, that everything will end, doesn't retroactively erase them. They happened. They're happening. And in the 10 to the power of 100 years it will take to reach heat-death, countless other experiences will happen. Trillions of beings might live and love and create and discover. Stars will illuminate worlds. Minds will ponder mysteries. Even as entropy increases, even as the universe marches toward equilibrium, there will be beauty, complexity, meaning. Not forever, not even for very long, on cosmic timescales. But it will exist. This is what we have, the flame. Brief, fragile, burning against a darkness that will eventually consume it. But burning nonetheless. Entropy is not the enemy. Entropy is the context. It's what makes change possible, what allows for differences in temperature and pressure and chemical potential. Without entropy gradients, nothing could happen. Time would be meaningless. We wouldn't exist. The heat-death is not a tragedy. It's a boundary condition, a fact about the universe's initial state and its laws of physics. Calling it tragic is like calling gravity tragic because it pulls us down. It's simply what is. What matters, what can matter, is what we do in the meantime. Boltzmann saw the heat-death coming and it drove him to despair. But he also created a framework for understanding thermodynamics that revolutionized physics. His despair was real, but so was his triumph. Hawking understood that black holes evaporate, that information might be destroyed, that the universe faces oblivion. But he also showed us that black holes have temperature and entropy, that they're not separate from thermodynamics but integral to it. His body was imprisoned by disease, but his mind roamed the cosmos. You are not these giants. You're an ordinary human, living in the early moments of a universe that will last for incomprehensible durations after you're gone. You will die. Everyone you know will die. Humanity will probably go extinct. The sun will swell and die. The Milky Way will collide with Andromeda and eventually fall into a black hole or be flung into the intergalactic void. All of this is true. None of it negates the value of your life, your choices, your experiences. Because here's the final secret, the truth that entropy can't touch. Meaning is not found in the universe. It's created by minds like yours. The universe doesn't care about you. It doesn't care about anything. It's indifferent, mechanistic, following laws that have no purpose or goal. But you care. You can create purpose where none exists. You can impose meaning on the meaningless, carve out islands of value in an entropic sea. Every act of love is a rebellion against entropy. Every work of art, every scientific discovery, every moment of beauty or connection or understanding, these are local, temporary decreases in entropy, achieved at the cost of greater increases elsewhere, but real nonetheless. You are an entropy engine, yes. But you're also a meaning engine. And the meanings you create, the experiences you have, the thoughts you think, the connections you forge, are as real as the stars, as valid as the mathematics, as true as the second law itself. When the last light fades, when the final silence descends, there will be no one to remember any of this. The universe will not care that we existed. But we exist now. We care now. And that is enough. The universe is dying. It has been dying since it was born. But in the space between the beginning and the end, in the brief interval where entropy is increasing but hasn't yet reached maximum, there is us. We are the flame, brief and bright and beautiful. And we burn.